Hey, AB Calculus, it is Mr. Canfield. Today we're looking at chapter 28, the accumulation function. We're going to see how far we can get in maybe like 15, 20 minutes or so, and then we'll break it up into another video if we need to. So we've learned that integrals are the antiderivative, and we've also learned that a way to represent an integral is area. So just like derivative is slope, integral is area. So if I said, hey, take the integral of this function f of t is equal to 2 from 0 to 5, the integral from 0 to 5 of 2 dx is literally just equal to the area of this rectangle, which is, 5 times 2, which is 10. But wait, what if you do the calculus? Well, the integral of this is 2x from 0 to 5. Plug in the 5, you get 10, minus, plug in the 0, you get 0. Oh, wow, it's 10. Wow. Oh, yeah, this is worth mentioning. I did like x in here, and it's like, this is t, this is f of t. Realize the equation of the graph of f of x is equal to 2 is the same as f of t is equal to 2 or f of k is equal to 2. Whether we use x, t, k, w, x, I already did y, z, now I know my ABCs. It doesn't matter what letter you use. The variable doesn't matter. The graph's a horizontal line. We're used to using x. I used x here. So if we had this, 0 to x, f of t dt, it looks different. It's not. It's really saying, hey, go from 0 to a of f of x dx. Like this, the integral is normal. There's a variable up here instead. Kind of weird. The reason that we're doing it this way is we're making a function of x that's like, we're turning area into a function. That's why they call it the accumulation function, because it's the area function. So what we can do is figure out, essentially, we can figure out how much area have we accumulated by a certain x value. So like, I know that from here to here, I get 10, but how much area have I accumulated by the time I've reached only 4 instead? Well, hopefully you see that's 8. Or by 3, we've only reached 6, or by 2, we've only reached 4, by 1, we've reached 2, and by 0, we've reached no area yet. That's all this is saying. It's saying from 0 to here, how much area have we accumulated? So this is part of the power that we have in calculus, is with integrals, we're going to be able to figure out how much something accumulates over time. And you know, when we're doing stuff with money, this is a really helpful tool. All right. So this is worth mentioning too. So going from 0 to x of f of x dx, this notation here, this is why we change it to 0 to x of f of t. We're saying like, okay, so for this integral here, you know, we're thinking about this integral separately from our situation of going from 0 to x. And that's why the f of t dt, if it doesn't make 100% sense, that's fine. I hope my explanation helped a little bit, or you know, maybe reread this section here if that would be helpful. You don't have to fully understand why we don't write it like this to be able to do it. Big deal is 0 to x f of t dt is just the way that we write this. So to the right is the function f of x is equal to 2x. let's calculate the value of the accumulation function from 0 to 4. So we're going to accumulate up to 4. And there's a couple of ways that we can do this, like we did earlier. You can actually calculate the integral and you can go through and find it, or you can geometrically get the area. It doesn't matter. Neither one is more correct. It's really whatever you're more comfortable with. So honestly, I do think for this, finding the integral will be easier, because what's the antiderivative of 2x? It's x squared. But remember, we're going to write it the silly way. We're going to say 0 to x 2t dt. And so now I can say the integral of that's t squared, going from 0 to x. Oh, so if I want to find, if I want to find, I don't know, let's not plug anything in for x yet. Let's just plug in x. So then we get x squared minus 0 squared. If I want the area up to any one of these points, all I have to do is plug in the x value that I want and square it, and that's going to be the accumulated area. So plug in 0, I get 0, plug in 1, I get 1, plug in 2, I get 4, plug in 3, I get 9, plug in 4, I get 16. And if you're like, that does not look like this, well, notice the scale. He's going by 2s vertically. Plot those values on this graph. Connect them with a smooth curve. The curve should be familiar. Wait, oh. All right, so I put the cart before the horse a little bit. Maybe I'm telling you things that I wasn't supposed to quite tell you yet. Integral and area. And, well, hey, what is this? So 0, 0, 1, 1, 2, 4, 3, 9, 4, 16. If you're like, wait, what is that? Guys, this is the graph of x squared. The accumulated area of a function is its antiderivative is, wait, what? So in this situation, like the derivative of this is that line, and the accumulated area is the other function. So like the slope of this curve is this line. Like here my slope is, whatever that is. Turns out that the slope there is 6. And the accumulated area is the function. That's a crazy relationship. I never would have guessed that. Did you guess that? Were you like, oh yeah, so sure, slope is the derivative, and if we were to reverse slope, we get this accumulated area. No, I mean, I wouldn't have guessed that. Maybe you did. And if you think about it, if you like reverse what a rate is, a rate's like distance over time, right? Like, so reverse the time and you collect that distance back up. So, all right. I love this. This is the best. This is, oh, you're gonna love this. You're gonna love this. You're gonna hate this. No, it depends on who you are. So, remember we took this integral a few minutes ago, right? We got x squared. Well, x squared minus 0 squared, so just x squared, right? What's the derivative of x squared? So, if this isn't like, let's go back. Let's go back. We had 0 to x 2t dt, right? Took the integral, take the derivative of that integral, this turns into this. This is one of the fundamental theorems of calculus, that the derivative of the integral is just the function. Derivatives and integrals reverse each other. So that will be examined in the next chapter. Wait. Why am I doing this? I just filmed a video doing this. So, hey, we've got more practice. Yeah, knock yourself out. I'm not doing these. And even 5, I don't need to do 5. Yeah, these are all good. These are all interesting problems. Like, they're worth thinking through, but you don't need me to do that. Oh, I'm stupid. Right. This is the homework from chapter 27. Okay. I was like, Stu, why are we going backwards in time? Sorry about that. Okay, here we go. All right. So, big F. So, I don't think I've told you yet. Big F is the same as the integral of little f. So, like, big F prime is equal to little f. So, for those of you that like to write in all caps all the time, you're not allowed to, okay? You gotta use lowercase f for regular f and big case F for integral of it. So here's our f of t. And remember, f of x and f of t, they're the same thing. We're switching them around so that we can keep an x in the integral bounds. Oh, and this is a snowfall problem. So this is a really good example because snow is such a tactile thing, and we know what happens. So snow falls at some kind of rate, and it accumulates, and then it melts. So like here we're accumulating snow. We accumulate snow all the way up until we hit 3. And then between 3 and 5, we can say some of the snow melts. So this is not the amount of snow we have at any given time. This is the amount of snow we are accumulating at any given time. So even though it's not snowing at t equals 3, there's still snow on the ground. We're just not getting any more, and we're just not losing any of it. So let's go through and calculate the amount of snow on the ground at different times. And we gotta pause. How much snow is there to begin with? If they don't tell us how much snow there is to begin with, the numbers that we come up with here are saying, well, given however much snow you started with, this is how much more or less there's going to be from what you started with. Let's see. Yeah, I'm not seeing anything. Okay. So at t equals 0, there's no new snow. At t equals 1, well, I see a trapezoid here with a height of 1, and then 1 and 3 here. So 1 plus 3 is 4. Divided, so that's a half, 4, 1, so 2. So this is 2. And this is, for my preference, I do like to, I mark up my picture. This is 3 blocks. That's a nice and easy one. Oh, here's a nice and easy one too, -1 blocks. So then I got a triangle, 1 by 3 divided by 2. And then, since I'm required to do every single second, I may as well just break these up. So this is 1 by 4. Oh, okay, so it's 4 over 2, so 2. And then that's another one, same thing. This is a, triangle, 1, 1, so it's a half. Whoa, 6.5 is in there. This is a height of 1, but base of a half. So this area here is 1/4, and so this one, same deal but negative. This is -1/4. All right. So now all right. So at 1, we got 2. From 1 to 2, we add 3 more to that. So now we have 5. It's not just 3. And this is not 3 halves. This is, take that 5, add on 3 halves, right? Because it's how much have we accumulated. That's what the integral from 0 to wherever we stop is the amount that we accumulate from 0 to wherever we stop. So 3 halves is 1.5. So 6.5 or 13/5, right? And then at 4, we've lost 2. So there's been like ultra melting or something. Maybe these are over days or something like that, right? So in one day it got really warm, we lost 2 inches. And oh, interesting, right? We lose 2 more inches the next day, even though like it's going up. So we don't want to think about these as being like uniform things, right? Like I didn't lose 2 inches all at once. I lost a little bit and then I lost a lot. And I'm still losing a lot, but now I'm only losing a little bit. And so over these 2 days, we lost, oh, these are hours. I think days makes more sense with this because losing that many inches, but anyway, over these 2 time periods, that's what happens total. More happens at some points than others. Not super important right now, but worth thinking about. From 5 to 6, we tack on another 0.5, so we're up to 3. Then from 6 to 6.5, we tack on a quarter. But then we lose that quarter. And then we lose another 1. And so by the end of all this, we've accumulated a total of 2 inches of snow. We've gained some, we've lost some, gained some more, lost some more. Okay. So now, what if I wanted to find out the rate of snowfall at any given time? Because I remember earlier when we were saying at 3, it's not gaining any snow. The rate of snowfall. Well, if I want the rate of snowfall, can't I just take the derivative of my snowfall? So the derivative of my integral? Wait, the derivative, wow. The derivative of the interval, is that what? Right. The derivative of the integral just brings the x and you're done, right? So the integral's this, our snowfall's this. If you want the rate of snowfall, it's just f of x. It's just the y values here. If this is a derivative, then you just need the y values. This is a rate already. So this crazy mess is just 1, 3, 3. I'm literally just getting the y values from here, and that would be the derivative of our big F. At 3, we're 0. At 4, we're -4. 5, we're 0. 6, we're 1. 6.5, we're at 0. 7, we're at -1. And 8, we're at -1. And again, if this doesn't click conceptually 100%, it's okay. Give it time, and by time, like it could be years until it like, oh, okay, that's fine. Sometimes we don't get things until we circle back and see them again. Doesn't mean that you're doing anything wrong. So this is f of x, big F of x. These are big F prime of x. And this was the area of regular F. And this was just y value of regular F. Just an extension. If big F is the area of regular F, F prime is the y value of regular F, what would big F double prime be? Well, if you take the derivative of area, you get y value. If you take the derivative of y value, you get slope. So it's going to work the same way that things have always worked. We're just thinking about it in a slightly different light. Okay. Remember that we can determine information for when big F, I need to call this big F increases and decreases as well as relative extrema by looking at big F prime. Using the table above, make a sine chart of big F prime and determine intervals where big F increases, big F decreases, and when big F has a relative max and min, and what those values are. Okay. So, sine chart time, big F prime. See, big F prime is 0 at 3 and 6.5. Prior to 3, big F prime is positive. In between 3 and 6.5, I missed one. There's 5 as well. Between 3 and 5, big F prime is negative. Between 5 and 6.5, big F prime is positive. And then after 6.5, big F prime is negative. So what we do is we remove ourselves from this situation. We just go, well, I have a thing, I can make a sine chart out of it, great. Well, if that's big F prime, what does that tell me about big F? Well, it tells me that big F is going up, flat, going down, flat, going up, flat, going down, right? So it looks like big F is going to have a maximum at 3, and then another maximum at 6.5, and a relative minimum at 5. Right, if you follow what the curve is doing. Now it says what those values are. The problem is we don't know how much snow we started with. So big F of 3 is 6.5, but we don't know if that's 6.5 inches on dry ground or 6.5 inches on top of 12 feet of snow. Like there's no way to know, but you know, for the we can say it's 6.5. Yeah, I was just double checking that there wasn't some initial condition. Normally they'll give you an initial condition and they'll say, okay, so at the start of our measuring, we had 3 inches of snow, you know, that sort of thing. So if we started with 3 inches of snow, well then at time equals 3, we've got 6.5 on top of those 3 inches, so we'd have 9.5 inches. Like that, that's really what we're saying. Okay. Remember, we can determine information about the concavity of big F by looking at big F double prime. So big F double prime, the concavity of big F double prime is the slope of this picture. And it can be helpful to write these things out to think about them. You know, because to get from big F to big F prime, we did area to y value, or you know, we took the derivative of this. And the derivative of y value is slope. The derivative of slope is concavity. So we actually can construct a sine chart for F double prime then. Check it out. F double prime. F double prime is going to be the slope of this picture, right? So F double prime here is positive, 0, negative, negative, positive, positive, negative, 0. So I'll finish up this part and then I'll cut the video here and we'll continue on next time. So let's see, F double prime. I feel like I need a table first. So I'm gonna, because I need to know that my different values of F double prime. And for me, like a slope of 2 and a slope of 3 doesn't look crazy different. And if I'm just dealing with concave up and concave down, I don't care a ton about exactly what numbers those are. So at 0, we're going to have, well, between 0 and 1, we've got a positive slope. Between 1 and 2, we've got a 0 slope. Between 2 and 3, we've got negative, and the negative slope goes all the way until we hit 4. And then between 4 and 5, we have positive slopes. And we have an undefined slope at -4. So from -4 to 5, we've got positive slopes. At 5, we have another undefined slope. Oh, actually, looks at 3, we have an undefined slope as well. So 5 to 6, and then at 6, we have an undefined slope. And then 6 to 7, we have negative slopes. At 7, we have an undefined slope, and then at 8, we have a 0 slope. So if I was to talk about concavity, so we have these weird undefined slopes. Those could all be like, remember, an inflection point is when you change from positive to negative concavity. So it looks like our inflection points are going to be here, because that switches from negative to positive, and here. We got an inflection point at 4. So 4, we have an inflection point. I'm going to remind myself with a dotted line. And then at 6, we have an inflection point. The other places that we have 0 concavity, we're going to have like a flat line for those parts. And then when we have undefined concavity, a lot of times it's like just a vertical section. So I am going to plot my y values. So 0, 0, 1, 2, 2, 5, 3, 6.5, 4, 4.5. These dotted lines are not appropriate. These are for my own reference. These are inappropriate dotted lines. 5, 2.5. 6, 3. 6.5, 3.25. 7, 3, 8, 2. Okay. So from 0 to 1, we have concave up. So it needs to look like a cup. From 1 to 2, we have no concavity, so it needs to be flat. From 2 to 3, we have negative concavity, so it needs to be concave down. Then from 3 to 4, still down concavity. And then look at that. There's a perfect inflection point for us. So concave down to concave up. At 5, we are still concave up. We're concave up all the way to 6. Remember, I'm just following positives and negatives here. At 6, we've got another inflection point. So now we're concave down. Concave down. Up until we hit 7. And then from 7 to 8, we are concave 0, so we're flat. So this was supposed to be flat, and this is supposed to be flat. Whew. I feel the strain a little bit from that analysis, but we can do all of that from this original graph and construct this. So here's the thing. Let's say instead we started with 3 inches of snow. All you'd have to do is take this graph, move it up 3, boom, you got your new amount. It's pretty cool. All right, next time we will do some more practice with some more ideas. Next video should be pretty short. So, bye.